Morning, everybody. So I've been asked to make a video regarding the F-test and basically show where the numbers land and so forth in the F-test on the way ALEKS presents the printout. And to be fair, this is a pretty standard looking printout for the ANOVA test. And so I'm going to break this down real quick and point out where the numbers come from. And then I will have hopefully enough time, because I only have 10 minutes, to be able to establish the null and the alternative and try and set up the distribution and so forth so you can see it. It'll be a little sloppy and rushed, and I apologize because I only have 10 minutes. So I will put this problem in a link above the video. So very quickly, it says, much is still to be learned about the relationship between sound frequency and loudness. One way to study the relationship between sound frequency and loudness is to have listeners perform loudness judgments for tones of different frequencies. For each listener, the output of these judgments is a number measured in sones that gives the loudness of the tone relative to the loudness of a reference tone. Suppose that you have in front of you data from an experimental study in which listeners were asked to perform such loudness judgments for tones of various intensities and frequencies. The listeners were divided into non-overlapping groups according to their hearing ability, normal unaided hearing, some hearing loss at certain frequencies, normal aided hearing, etc. It works out, and I'll be able to explain this in a second, that there are 4 categories. The data give the zone measurements for each of the listener. You perform a one-way independent samples ANOVA test for the hypothesis that the mean zone measurement are equal for the different population of listeners presented in the study. All right, so we have 3 degrees of freedom in this. I say 3, I mean 3 different categories. We have the total, error within, and the treatments. So this is the degree of freedom for the numerator, this is the degree of freedom for the denominator, and this is the total degree. Now, again, your author uses a slightly different notation, but degrees of freedom numerator, that's supposed to be an n, forgive me, is equal to, and I use the notation k minus 1, where k is the number of categories. So if you have 3 is equal to 4 minus 1, you get your k to be 4. So the number of categories we're looking at is 4. Now, the next thing is that the degrees of freedom for the denominator is the grand total of observations, like how many total observations there are, minus the number of categories. Well, we worked on the categories. We got that to be 4. Degrees of freedom for the denominator is that second box, which is where the 64 is. And so we find our n, when we solve this equation, to be 68. Okay? So it asks the question, how many listeners are there, or how many listeners total were tested in the experiment. That's how we get the 68. Now, the F statistic, and in the problems that I give you on the test, I have you put the data in L1, L2, L3, and so forth, and you run the ANOVA test. And then the calculator will generate, it doesn't match the way this looks, but it gives a printout and gives the same information. And what you end up doing to get the F statistic is actually take 0.38 divided by 0.32. And that will give you your F statistic, okay? I debate whether or saying this, but if you take your 1.13 and you divide it by 3, you get your 0.38. And if you take your 20.16 and you divide it by 64, you get your 0.32. So this number divided by this number gets you here. this, this number divided by this number gets you this number divided by this number gets you this. I said it reversed, so my apologies. And then you divide these two to get your F statistic. So 0.38 divided by 0.32. And you get your 1.1875. Okay. Now, the next question asks that the population variances, we need some representation of the population variances. And it works out that this is the value that you'll use. This box is that answer, okay? Now, let's travel down a little bit farther. And again, we're using alpha's 0.05, and we have our two sets of degrees of freedom. So I'm going to bring up the table that I sent you guys. And I apologize for it being on an angle, but you've got to first make sure that you have the right alpha. And so I've grabbed the 0.05 table. The degrees of freedom for the numerator are 3. The degrees of freedom for the denominator are just slightly more than 60. So our critical value is the 2.76. Okay, so you're taking the two sets of degrees of freedom and you're finding where they match. Now, I'm gonna very quickly write this because I've only got a couple minutes left. So your null is, briefly, all means are equal. Our alternative is at least one is different, okay? Our distribution is an ANOVA distribution, which is a right-tailed test. We've found our critical value to be 2.76. We've run our test statistic, and we've had it land at about 1.1875. Now, when you run this on your calculator in the way that I have it set up, you'll get a p-value out of it. And you compare your p-value to your alpha. Now, your alpha is this large. It's this area right here. And your alpha is 0.05. Now, our p-value is from our test statistic out into that same tail, so it's larger. Forgive me. It's from this test statistic out into the tail. So our p-value is bigger than our alpha. I don't have the p-value, and I've got to run it off the raw data to be able to get the p-value correct. So what are we claiming here? Let me just double check what the claim is. So we're trying to test to see that the mean are equal for the different populations. So this is our claim. We are claiming this one. So again, our calculator will give us the p-value. That's always required, but we don't have it because we don't have the raw data. There is a way using an F calculator to be able to get that p-value, but I don't require it. Require you using that calculator because your calculator generates your p-value for you. So, number one, based on the location of the test statistic, we fail to reject the null at alpha's 0.05. Now, the claim is that they're equal. Well, the location of the test statistic is supporting the claim. So we have sufficient evidence. I'm just being brief here, so sufficient evidence to support the claim. Sorry for the bad camera work. I'm trying to move quickly so we can get this in. All right, have a good one.